This last lesson in this module covers the practice of phosphorus-sorbing filters. Don't forget, if you're interested in the other conservation drainage practices that I did not cover with the short lessons in this module, the practices of controlled drainage, drainage water recycling, and denitrifying bioreactors, they each have their own full modules available later in this series. You'll remember from earlier lessons that there are several forms of phosphorus to be concerned about in agricultural runoff or agricultural drainage water, both particulate phosphorus and dissolved phosphorus. You'll also recall that our concentrations of phosphorus in ag drainage water tend to be very low numbers, and correspondingly the associated losses of phosphorus draining from our fields in terms of kilograms of P per hectare are essentially agronomically inconsequential because they're also very, very low numbers. But you'll also recall that these very low concentrations or losses from agricultural sources can lead to very severe aquatic problems. And that's why our recommended nutrient criteria for phosphorus, both on the national level and here in Illinois with our nutrient criteria, tend to be very low for phosphorus, often reported in micrograms per liter. And of course, we're particularly concerned about dissolved phosphorus because it's immediately biologically available compared to particulate phosphorus and can immediately cause negative aquatic impacts with eutrophication. A compounding factor here from the agricultural perspective is that most of our current conservation practices address erosion or address sediment transport and aren't necessarily intended to reduce dissolved phosphorus losses. Dr. Chad Pinn, who's really one of the world's expert in phosphorus-sorbing filters, really put it best by saying, the temporal disconnect between water quality goals and the length of time that legacy phosphorus sources remain a viable source, the difficulty in controlling dissolved phosphorus loss from soil, and the immediate bioavailability of dissolved P justify investment in a new kind of conservation practice to specifically address dissolved phosphorus. So, enter the practice of a phosphorus-sorbing filter, or sometimes called a P removal structure. This is a relatively new, edge-of-field, constructed conservation practice that provides a metal cation to react with dissolved phosphorus to create an insoluble compound either by adsorption or precipitation, so chemical processes, and in doing so, the phosphorus-sorbing filter reduces phosphorus loss. There are really three components for getting a P filter or a phosphorus filter right. First of all, you need enough filter material to remove the phosphorus that you want to remove. So these tend to not be small structures. You also have to allow the water to flow through the media at a high enough flow rate. And you see like this example at the caption at the bottom of the screen, the design flow rate was 400 gallons per minute. That is not a trickle. That's pretty fast. So the water has to be able to flow through the media at that sufficient flow rate. And then the media will eventually get saturated with phosphorus because this is a chemical process that happens on the surface of the phosphorus-absorbing medium. All those surface sites will eventually get saturated, and so you have to plan in your design to replace the media. This is not a forever practice. Replacing the media is part of the process for this practice. Phosphorus-sorbing filters work by, like I said, chemical adsorption or chemical precipitation. P-filter media usually contains either one or a mixture of aluminum, iron, calcium, or magnesium. And you see examples of phosphorus-sorbing materials there in the picture. Starting with calcium and magnesium, because phosphorus mostly reacts with those two to form a precipitate like calcium phosphate or magnesium phosphate that's opposed to absorption, these two elements actually must be dissolved in solution inside the P filter to be effective for P removal. And then one nuance about the iron and aluminum type of P filter medias, those actually work better at pH less than about 7.5. Otherwise, the mineral surfaces will have fewer positive charge sites on the surface to provide the ligand exchange absorption, which is how aluminum and iron remove phosphorus from water. So that's a little bit of the chemistry. There's a variety of considerations when you're choosing your phosphorus-absorbing media, which this flowchart illustrates relatively well. Obviously, one of the first things to think about is the effectiveness of the media. How well does it actually remove phosphorus, usually in terms of like grams of P removed per kilogram of media. One important trade-off from the engineering side is that because this is a chemical reaction that has to do with available surface area of the particles, you might think that you want for your media a really, really small particle size, like something like a powder. Powders have really high surface area because the particle sizes are so small for powders. However, you still need to be able to get water through the media. And so there's a trade-off of having small media where you have a lot or a sufficient surface area, but not having media so small that you can't force water through it. The two pictures that I'm showing there are an experiment that we did a couple years ago. The top is a larger particle size. It's an iron containing acid mine drainage treatment residual. And we compared that with a steel slag, which had a much smaller particle size. And so we could actually move water through the MDR, or that orangey material on the top. We could move water through more quickly through that material than the steel slag because the particle sizes were larger. Coincidentally, the MDR on the top picture actually also had a higher phosphorus removal ability, and so it just turned out to be a much better material overall, although it's not available everywhere. Which plays into our next factor. You want to consider cost, and cost involves the transport factor and the availability. So for example, that MDR in the last picture, I wouldn't recommend everyone use that everywhere because that was from a mine drainage treatment facility in Pennsylvania. So that'd be very expensive for someone in California to try to use that material. So obviously cost plays into your selection criteria. And then you don't want to use phosphorus absorbing media that's going to leach heavy metals or other harmful contaminants. Obviously, this is a water quality improvement practice. Industrial waste byproducts like steel slag are a very popular option for this kind of P-sorbing filter because of their widespread availability and low cost. They're often free. Steel slag is a waste byproduct. But you definitely need to test these media in the lab before you go full scale with them to make sure you're not leaching some of these harmful contaminants. There are also commercial products available for phosphorus absorption, but these tend to be very cost prohibitive for an agricultural purpose, like treating pee and runoff or pee and drainage. Last point on phosphorus absorbing filters, they're typically designed based on a performance criteria of how much phosphorus you want to remove. So these are a very engineered design practice. And so that's the answer for how well do phosphorus absorbing filters work. They work based on whatever you design. They work to meet a criteria, whatever you design them to. If you want a phosphorus filter that removes 100% of the phosphorus coming from a certain water source, you might need a really, really, really big filter to do that. So we typically don't design for 100% P removal, but this is an engineered practice allowing that flexibility. I want to end by saying dissolved phosphorus is a really tricky water quality problem. And in the end, edge of field replaceable P media in phosphorus absorbing filters might be really one of our only ways that we can deal, especially with sources of legacy phosphorus in our landscape. See you next time.